Hello and welcome to Hollow State Homebrewing, the art and science of building stuff with thermotrons. I'm Grayson Evans, KJ7 Uncle Mike. I've been a ham off and on since 1963, and I spend most of my ham time restoring 60 era thermotron gear, homebrewing thermotron gear, and writing about it. In this presentation, I'm going to show you some easy and quick techniques to homebrew with thermotrons and pass along some tips and ideas I hope you can use. Now, I know some of you might be a little unfamiliar or even uncomfortable with the term thermotron. So let's get that straight right away. The thing in the upper right corner is a valve. The thing in the lower right corner is a tube. And if you look these terms up on Google, that's exactly what you're going to see. And this, ladies and gentlemen, is a thermotron. If engineers could come up with the name transistor, which back then I'm sure sounded cool, I can't believe they couldn't do any better than tube. At least RCA finally called their new miniature metal ceramic tubes new Visters. But that was too late. For the next 20 minutes at least, this is what I mean when I say thermotron. Some of you might be thinking, why would I want to build new projects with technology that's obsolete and nearly 100 years old? Why indeed? Let me give you my top 10 reasons that I think will clear up this question for you. Starting at number 10, thermotrons were actually used in alien spaceships. Several strange thermionic devices were reportedly secretly supplied to RCA by the Army in 1939, recovered from an alien craft. RCA introduced the acorn tube in 1940. Coincidence? Number 9. Homebrewing with thermotrons builds character. There is high voltage and high power. Lots of fun. Number 8. Thermotron equipment is easy to build. Check out how open and easy it is to get to the parts in the chassis on the left. On the right, we have surface mount. It was designed for robots. It was never intended for old guys like us to attempt to build by hand. That's insane. Number 7. Thermotrons will generally outperform solid-state devices in most RF applications, especially those manufactured near the end of the 1960s. There's just no solid-state equivalent. For example, for the Amperex developed 7788, one of the highest gains, lowest noise amplifiers ever built. Number 6. They're never really obsolete. Any tube manufactured after 1930 is still available today at reasonable cost. Number 5. They are electrically rugged. They'll take large voltage variations in stride. Number 4. Thermotrons and thermotron gear smells good. Open the lid on a 1965 Collins 75A4 and take a whiff, and you'll see what I mean. Ham radio perfume. Number 3. Thermotron characteristics are generally more linear than transistors. This is true. Check it out. And number 2, they're static discharge proof. But the number 1 reason is simple. Thermotrons are beautiful, a marvel of industrial engineering. Definitely can't say as much for these little things. They all look the same. Can't tell them apart, and not very interesting to look at. Now that you've had enough reasons to build something with thermotrons, let's get into building. Even though I've built thermotron equipment for many decades, I was always intimidated by the metalwork. Thermotron gear always seems to be built the same way, using standard aluminum chassis, even for small projects. I know this puts a lot of people off, including me. While I admire the homebrew builder that can do the kind of work you see in the photo on the right, which, by the way, is a version of the famous HBR11 receiver, I'm not very good at it. And it is certainly not very prototype friendly. What I would call modern homebrew construction, shown here, is the technique of choice in the QRP community. I call it glue and go construction, just a copper-clad board with various types of pads glued down. In the past, it's been difficult to incorporate thermotron sockets, so I've been experimenting with techniques of QRP solid-state construction applied to thermotron construction. Copper-clad boards as the chassis, glue and go construction, lots of soldering aids, easy prototyping, quick changes, and quick prototype to finished product options. But to get there, I needed some kind of solder pad for thermotrons. Fortunately, several years ago, Rex Harper, W1REX, developed a set of thermotron socket pads he calls Me-tubes. His Me-tube panels consist of 10 solder pads, especially designed for mounting thermotron sockets. The panel is V-scored for breaking off single-tube pads. The pads can either be superglued to a piece of copper-clad stock or mounted using screws and standoffs. The panel has pads for several common thermotron types: miniature 7 and 9 pins, octals, compactrons, and acorns. Yes, acorns. I found the best sockets to use are printed circuit style, shown on the left. They provide a large pin area to bend out and solder to the pad like you see on the right. Ceramic versions of these sockets are readily available for online stores for about $1 or $2, but the best place to find them is still hamfests and flea markets. I pre-mount a dozen or so of the 7 and 9 pin sockets on Me-tube pads, so I have them ready to go when prototyping. They can be glued on a larger copper-clad board and mixed with other pads to hold discrete components. The nice thing about the pads is that they provide plenty of room to tack solder lots of parts to a single pin, making it easy to add or remove the parts. This is a lot easier than using the traditional tube socket pins. The photo left shows a compactron pad using a chassis mount socket and a 9-pin pad on the right. Prototyping thermotrons in this way is fast. No more punching holes to hold sockets in an aluminum chassis and mounting terminal strips and standoffs. This is the fastest transmitter I ever built. One tube, 100 milliwatts output in 1 hour. It uses a low voltage space charge thermotron. Needs only 12 volts on the plate, furnished by the 12 volt wall wart power supply. A good example of low voltage thermotron project. It took me longer to make a contact than it did to build it. I've got a big stock of surplus Acorn thermotrons, 954s, 955s, and so on. They're cheap and make really interesting looking projects. The big problem with Acorns is the socket, a special ceramic ring with 5 clips that hold the pins. These are pretty much extinct. But the Acorn pad supplied with the Me-tube provides an alternative. To my surprise, the pins on the Acorn are easily solderable directly to the pad. The pads can be glued to the edge of an existing board, as shown in the photo, or a 12mm hole can be drilled in the board to accommodate the size of the Acorn. But it's still nice to be able to have the thermotron on the top of the board for a more finished look. To do this and still use the Me-tube pads, the thermotron has to be mounted on the other side of the pad by mounting the socket through the pad. This requires making a hole in the center of the pad to pass the socket through, and then soldering the pins in the usual way. This is way easier with PC mount sockets like you see here. This is an example of a compactron socket mounted right side up. And this is what it looks like completed, ready for installation on a chassis. This is another example of front-end beam deflection mixer module. The board was cut to fit an aluminum chassis. The board flips over for mounting to the chassis. There are no holes in the chassis except for the screws to hold the board down. Another example of right side up thermotron mounting on a prototype test board for crystal filters. Note the acorn mounted through the board. I also glued a small plug board to the center to allow me to easily swap filter components. The board works great. My filter design, not so good. Loved using the plug board, gonna do that more often. Don't get me wrong, you can still use regular thermotron sockets, as in this example. This reminds me of something I wanted to recommend. Wire the filament string first. That way you can test the tube filaments and wiring before adding any other parts. This is what that board, an IF strip, looks like getting wired up. And this is how it looks on top. Since I wanted to use shields on most of the thermotrons, I used the shield-ready sockets. One thing you'll need to experiment with thermotron sockets is a good high-voltage power supply. It should furnish up to 300 or 350 volts at about 125 milliamps, and should provide filament voltages of 6 and 12 volts at 2 amps or so. You can find one of many Heath high-voltage supplies, like the IP17 shown on the left, my favorite, on eBay or at Hamfest. Of course, you can build your own, like the one on the right I built. Email me for the schematic if you're interested. This is a 40 and 20 meter AM CW QRP rig using modular copper-clad board construction. The front panel is a double-sided board. It consists of 3 modules, also built on copper-clad board. The VFO on the right, the AM modulator in the middle, and the output amp on the left. The aluminum chassis is only used for interconnection wiring between the modules. Using modules allows easy circuit changes. I've already changed the modulator and output board to better designs. I love playing with the Arduino. Total nerd toy. A while back I got interested in interfacing one to thermotron circuitry to see what I could measure or control. It turns out that the Me2 pads fit between the headers on the prototype shield exactly. The first project was this interface to a simple crystal oscillator. The digital outputs can easily handle the cathode current to key the oscillator, and one of the analog inputs was used to capture the output waveform. It looks like this. As long as the grounds are common and the filament voltage is isolated, it's no problem as long as you're careful where any high voltage connects. Don't want to blow up one of these Arduinos. My other fun project was to control and monitor a simple QRP transmitter. This is the 100 milliwatt 1-hour transmitter I showed you earlier. The Arduino is used to key the oscillator to send code, but it let me play around with monitoring cathode current of the output section while adjusting the bias voltage on the space charge control grid. It worked. This got me interested in building an Arduino-controlled thermotron curve tracer, a project I started, but I had to put on the shelf. Oh well, so many projects, so little time. I'm sure you're familiar with the problem. The other interesting aspect of thermotron homebrewing is there are so many types of thermotrons to experiment with. The Acorn I've mentioned before. It's perfect for VHF and QRP projects. The new Vistor, developed by RCA in 1959, is the closest thing to a transistor that the thermotron era ever produced. RCA made a couple dozen different types. Thousands were used in TVs and military VHF and UHF equipment, and they're still very available and quite inexpensive. The Magic Eye thermotrons are good, clean fun. They add a totally cool retro touch to any project that can benefit from a tuning indicator. Many young hams have never seen one before. Now, if you like to build really small, they're the sub-miniature tubes, used in a variety of early low-power applications where space was limited, such as early hearing aids and missiles. Raytheon was the biggest producer and the biggest customer during the Cold War. Originally developed by GE for the color TV market in 1960, compactrons are the closest thing to an IC you'll ever find with a filament. They combine 2, 3, or 4 functions in one envelope. There are at least 150 different types, and most still available at low cost. If working with higher voltages like 250 volts makes you uncomfortable, there are plenty of thermotrons designed to operate at low voltage, and specifically at 12 volts. The little 1 thermotron QRP transmitter I showed you earlier has a single 12-volt tube. The beam deflectors, such as the 7360 from RCA or the much improved 6H88 from GE, while originally designed for TVs as FM detectors, make very good mixers, modulators, and detectors. The 6BN6 is a gated beam thermotron, the only one of its kind. Originally developed for FM receivers, where it combined the function of limiting amplifier, quadrature detector, and AF amplifier. It makes a great product detector. I have one in the IF strip you saw earlier. If you're really interested in learning more, especially how to design and build thermotron circuits, the best source, if I may say so, is Hollow State Design by Grayson Evans. It's available from lulu.com, eBay, Amazon, Electric Radio Magazine bookstore. You can always just type in Hollow State Design in Google. Other great sources of info include Electric Radio Magazine, Sprat, the GQRP Quarterly, the Tube Lore Book, and of course, old issues of QST, especially 1950 through 1970. If you're an ARR member, you can search the QST archives by keyword. For example, if you want to see any article that used the 6BN6, just type that in. It works great. That concludes Hollow State Homebrewing. I hope you enjoyed it and learned something new. If you have any questions later on or want help debugging a thermotron project, just email me. Glad to help.